Hello everyone. So today we are going to discuss about the magnetics design. In magnetics design, basically there are a few primary constant. One of them is the peak flux density, which is Vmax. So if peak flux density, every designer he want to keep as higher as possible, but since this is dependent on the magnetic material, so we have constant. We cannot go beyond certain limit, which is defined as a Vmax, because this will lead to core losses and saturation. So if we go beyond the defined limit of Bmax, our component which we are designing will not work as we require, and ultimately the core losses will go very high, and the components will lead into the saturation. Second constant is the peak current density in the winding, which is called as Jmax, and this is also again depends on the winding material. So different material will have different maximum current density which they can handle, and in magnetics design we should take care of this. We should not design any components which is crossing this max limit, otherwise this will lead to excessive resistive loss, and resistive loss will lead to the heat, and ultimately our components will fail. So the wire with cross section of A, which is carrying current I RMS, this will have the current density J is equal to I RMS upon A conductor. So if we have a current limit, suppose we have chosen for some of our design as a current density J, we should make sure that our chosen current density must be less than the J max. So in that case, the criteria would lead us that the conductor size for the wire which we are going to choose must be greater than equal to I RMS, the current upon J max density. The next important point is the core window area. So core window area is the area which is available to fill the conductor inside of either inductor or transformers. So we have different kind of cores which will have different core window area where we fill the winding. And in case of toroids, this is the core window area where we are going to utilize for winding. And E core, this is the window area where the winding will be filled. And suppose that there are n number of turns of wire with cross section of area A. So this will lead to one of the conditions, because the winding area which is used for winding will not be completely filled. As you can see that there are certain gaps left out. So for this we will choose the fill factor Kw, and this is a fractional part of the window which is actually occupied by the conductor cross section. And according to this, if Kw Aw, the fill factor into the window area, must be equal to the number of turns multiplied by area of the conductors. So according to this previous constant, where we have considered that the conductor wire area must be greater than equal to the IRMS upon J max, with this equations it will lead that the area of the core window must be greater than equal to the number of turns multiplied by the IRMS current upon Kw fill factor upon J max. For transformers with multiple winding, the different winding must accommodate the different current, thus they must have the different gauge of wires. And according to that, in the last slide we have seen that Kw must be greater than equal to N1 into a conductor area of conductor 1, then N2 number of turns of winding 2, then area of conductor of winding 2, plus so on, uh, if we have multiple winding, and this must be equal to summation of Ny, a conductor Y. Suppose that if there are Y multiple output into the transformer, so equation must satisfy this condition. And however, the maximum current density must not exceed for any winding. Thus, we can say that the area of the winding core window must be greater than equal to the summation of Ny IRMSY upon Kw J max. This we'll see in the more detail in the coming slides. So for inductor core cross section area, A core, this how it will be selected and how it will we find out for inductor design, inductor core cross section. The core cross section must accommodate the peak induced flux without exceeding the maximum allowable flux density. So area of core cross section area must be greater than equal to the whatever is the flux it is going to pass through divided by the B max flux density. So for an inductor, the peak flux is proportional to inductance value into current divided by number of turns. And this will lead to that if we will put this phi value here, so area of core must be greater than equal to Li upon Nv max. Transformer core cross section area. How do we calculate the core area for core cross section area for transformers? So in transformer, the flux density may not exceed plus minus B max over 1 AC cycle at the worst case operating condition. As we have seen, this is the constant in the first page of the slides. So let delta T be the maximum excitation time for the primary. This will be at most half period, or Kc upon Fc, where Kc is the parameter reflecting the operating duty cycle of a power converter, typically 0.5 for the worst case flux density. So Faraday's law tells us that the change in magnetization flux density would be delta phi m equal to B primary upon N primary into delta T, which is equal to the B primary upon N primary. And this delta T, what we have seen here, the maximum excitation time for primary, this will be equal to Kc upon Fc. Therefore, the change in flux density delta phi m upon A core, because B is equal to the phi upon A, which will equal to the B primary Kc upon N primary Fc A core. This must be less than equal to the B max. And through this, we can conclude that this places a lower limit on the core cross section area. So core cross section area A core must be greater than equal to Kc B primary upon Fs is the switching frequency, number of turns across primary, and Vmax. And for sinusoidal operations, we usually consider Kc is equal to 0.225. Now the transformers or inductors, the design we do through two methods. One is called the area product method, another is called the core geometry method. So here we are going to discuss area product method. We now have the expression for minimum core window and the cross section as a function of maximum rating and operating parameters, which we have calculated before, which tells us that how big the device must be. So these expressions are used to express the useful magnetic core design parameters. We call this as the area product. So area product is equal to the A core cross section area, which is minimum requirement, and this is the conductor area AW. This is the core window area, sorry, where we do the winding. And from the previous equations, if we put the value of these both here, in case of inductor, it would be Li upon Nb max, and the winding area must be equal to the N IRMS upon Kw J max, which is equal to the Li peak into IRMS divided by Kw, which is the fill factor, and B max into J max for inductor. Same way the area product for transformers. If we take the both equation for core cross section and the window area, so this will lead to these equations for the transformer. Next we go for the core selection. How do we select the core for either transformer or for inductor? So from Bender datasheet, we select a core with the area product, where they defined the winding area and the A core area, which meets our minimum requirements what we calculated previously. So for a transformer, the number of turns for each winding is computed using these equations, and for inductor, the number of turns is going to be computed by using these equations. Since inductor air gap length is computed to provide the appropriate reluctance, because if we put the air gap, so then our inductance will be quite stable over the temperature range and over the and stable over the permeability. And this is the formula for the air gap. Lg equal to n square mu naught Ag upon L minus Lg. Ag area of gap upon area of core into mu naught upon mu core. Since area of gap is approximately area of core and mu naught is less than mu core, the gap length can be approximated Lg equal to n square mu naught A core upon L. Now we will take one examples. First we will consider for inductor that how to design the inductor. So this is the design specs which will be given from the design, and for whatever product we are going to design the inductor, either for the power supplies or for some other application, these are the minimum parameters which we require. What is the inductance value required for the circuit? 100 microhenry. And what is the IDC current if it is DC, and the inductor which have the DC and AC both, so like PFC inductors or converter inductor, different boost converter inductor. So we have to very precisely see the all these parameters. So IDC is 5 ampere, delta I 0.75 ampere peak to peak, which is riding on this DC, and then Vmax. So this data actually is coming from the core spec 0.25 Tesla, and Jmax is 6 ampere per mm square. So this is basically again also on the application, that how the product is having the cooling. Is it a natural cooling or forced cooling? And this is the limit which usually the experience, this comes through experience, or through some the specs which is provided us from the designer. And Fs is the switching frequency, which is 100 kilohertz, and Kw is the fill factor 0.5. So first we have to calculate the area product for the inductor. Area product, we know that it is inductance I peak I RMS upon winding fill factor, and B max flux density, and J max is the current density. So by putting all this value, we find out that the area product is 3587 mm to the power 4. And now we need to go back on the magnetic data sheet, and we need to see that which core is near to this our particular area. So we must take the product area not less than this but greater than this. So we have seen that the core PC26 by 16, this is having the core cross section area 0.39 centimeter to the power 4. So this is above our limit, beyond our limit, and we can choose this. And now we have to find out the different parameters. So A core here we can calculate, because we have here different dimension. So area of core, area of window, then AP product area. And now we can calculate that exact what is the n number of turns to achieve that inductor, because now we know exact core area 39540. So area of core, this is coming from here, and L is the inductance, which is the spec given. I cap is the peak current, P max is the maximum flux density, so 22 turn. Area of conductor we can consider by calculating IRMS current upon J max, so 5 by 6 0.83 mm square. And this, if we correlate with our AWG gauge wire, so we can come to know that it is a 18 gauge wire. And here we can author suggest that the 5 strand of 25 gauge of wire, if we consider this, then that will be sufficient. And next we need to calculate that what will be the air gap length. So air gap length Lg can be calculated, n square mu naught A power upon L. And number of turns we have calculated here. Mu naught is the permeability of free space, which is 4 pi into 10 to the power minus 10. A core is the core area, which is from here, and L is the inductance which is given already in the first phase. So Lg is coming 0.59 mm. So